So let's focus on problems involving finding the net electric field of system of charges. So let's begin our discussion with the first problem. Number one, a positive 200 microcoulombs charge is placed at the origin and a negative 300 microcoulombs is placed 1 meter to the right of it. What is the magnitude and the direction of the electric field midway between the charges and 3 centimeter to the right of the negative charge? So let's begin the solution of this problem with a diagram. So for instance, let's say I have a number line centered at point 0. So this point 0, a positive 200 microcoulombs charge is placed at that point. And 1 centimeter away from it, let's say from here to here, we have it to be 1 meter. So 1 meter away from it, we have a negative 300 microcoulomb point charge to be placed there. So the statement, find the magnitude and the direction of the electric field midway between the charge. So that refers to this point. So which implies that assuming this point is point P, and the distance between point P and the negative 300 microcoulombs is going to be 0.05 meter. Similarly, the distance between point P and the positive 200 microcoulombs is also going to be 0.5 meter. Right now, we can find their respective direction of the electric field produced by each of the charges. If you haven't watched my video on electric field, I recommend you click on the link that just pop out at the top right hand corner of this video, or you check out the video description as I explain everything you need to know about electric field. For positive charge, we know that the electric field formed by the charge at a particular point is going to extend away from the charge, while for a negative charge, the electric field produced by the charge at a particular point is going to extend towards the charge, which means the direction of the electric field formed by charge 200 microcoulombs will move towards point P because it has to move away from the charge. So I'm going to denote that as E sub 1, meaning the electric field of charge 200 microcoulombs, typically the positive one. And for the second one, which is the negative 300 microcoulombs, so since it is negatively charged, the charge will have to move towards, the electric field will have to move towards the charge, and therefore the electric field will be directed towards this way. And I'm going to denote that as E2. So now my main goal is to find the net electric field. So the net electric field will be the sum of the two other electric field. So E sub 1 plus E sub 2. It will be the sum of the other components. So a question I would like to ask you is, what equation should we use to find the respective electric field, E sub 1 and E sub 2? What equation of the electric field connects the magnitude of the charge, the distance between the charge and the given point, with the constant of proportionality in Coulomb's law? So it turns out that this is the equation to use in this case. So E sub 1 will be K multiplied by Q1 multiplied by or divided by R squared, and E sub 2 will be indeed equals to K multiplied by Q2, then all divided by R squared. Now it turns out that the net electric field will tend to be equals to K Q1 over R squared plus K Q2, okay, over R squared. So what I'm going to do right now, since the value of R and the value of K remain the same for both cases, then I'm going to factorize them out and have the net electric field to be expressed as K over R squared, then multiply by Q1 plus Q2. So at this point, I can begin the substitution. So therefore, the electric field, typically the next one, will be indeed equals, the value of K is 9.0 times 10 to the power of 9 divided by the radius is 0.5 meter. So we are going to square it. Then we are multiplying this with the sum of the first charge, which is 200 microcoulombs. So 200 microcoulombs in coulombs, we have to multiply with 10 to the power negative 6. So it turns out that these two zeros will reduce this 6 to the 4. And therefore, it's going to be 2.0 times 10 to the power of 4. So I'm going to write Q1 as 2.0 times 10 to the power of 4. Then I'm adding it with, for the second charge, Q2. It turns out that it is positive or negative 300 microcoulombs. So even though the sign doesn't really matter in this case, I just need to reduce the magnitude since I need to multiply with 10 to the power of negative 6. So these two zeros will affect this 6 to reduce to 4. And that will be 3.0 times 10 to the power of negative 4. So that's negative, my bad. Then plus 3.0 times 10 to the power of negative 4. Hopefully you can see that. Okay, I'm going to write that for easy visualization. So therefore, the net electric field is going to be equals to 9.0 times 10 to the power of 9, all divided by 0.5 squared, and multiplied by 2.0 times 10 to the power of negative 4, plus 3.0 times 10 to the power of negative 4. So that should be indeed equals 9.0 times 10 to the power of 9, all divided by 0.5 squared, then multiply by, so we can add this up since they are both associated with an index of 10. So that should be 5.0 times 10 to the power of negative 4. So at this point, I need to use my calculator to have my answer. So if you type that properly, you should get 1.8 times 10 to the power of 7. So the unit of electric field is Newton per coulomb. So you have to associate the unit with it to have a full mark. So this is the solution to the first part. So for the second part of this problem, we have to also find the magnitude and direction of the electric field when we have a point that is 30 centimeter to the right of the negative charge. Now I want you to note that electric field is a vector quantity, so the direction really matters. The reason why we are adding this and this together for the first problem, it's all because they are both directed towards the positive x-axis, and that is why no sign is changing. But for the second part, something will change. So let's begin. So I would need to draw the diagram. So this is Q1, for instance, and this is Q2. Q1 is said to have a magnitude of positive 200 microcoulombs, and Q2 possesses a magnitude of negative 300 microcoulombs. Distance between Q1 and Q2 is given as 1 meter. Now, we are to find the magnitude and direction of the electric field 30 centimeter away to the right of the negative charge. So it means we are going to move 0.03 or 0.3 away from the negative charge. So assuming I move 0.03, this 0.03, So I have a new point. Let's say this point Q. So I want to find the magnitude and direction of the electric field at this point due to Q1 and Q2. So that's what the question means. You might be wondering how I get to the point 3. The distance is given to us in centimeter, 30 centimeter. And to convert it to meter, what we are going to do is just to divide by 100. Then that will cancel it and result in 0.3. Okay, so meter. So what you need to know is that 100 centimeter is simply equals to 1 meter, and 100 meter is indeed equals to 10,000 centimeter. Okay, so when you are converting from centimeter to meter, you divide by 100, and when you are converting from meter to centimeter, you multiply by 100. So that's just something you want to keep in mind as well. So let's continue with the problem. So now let's figure out the direction of the electric field formed by each of these charges at point Q. So let's begin with the first charge, Q1. Since Q1 is positively charged, we know that the charge will tend to extend away from, the field rather, will tend to extend away from the charge, and therefore the electric field will move towards this direction. So I'm going to denote that with E sub 1. Now what about Q2, which is E sub 2? Where will the electric field, where will it be directed to? So this one is directing towards the eastern part. And what about Q2? For Q2, since Q2 is negatively charged, we know that the field formed by negative charge will tend to extend towards the charge, and therefore the charge will move this way. And right now, we can see that E2 is directed towards the western part. So therefore, E2 will carry a negative sign. And the net electric field will therefore be equals to E sub 1 plus negative E sub 2, which will result in E sub 1 minus E sub 2. So please make sure you are always very careful with the direction of the electric field. When it is directed towards the negative x-axis, you assign negative sign with it. When it is directed towards the positive x-axis, you associate a positive sign with it. So another thing you need to know is that to get the distance between Q1 and the given point, we need to add the distance between Q1 and Q2, and also in addition, distance between Q2 and the value of Q, because we can say that the distance between Q1 and the given point is from here to here. So therefore, R1 will be equals to 1.3. So that will be 1 plus 0.3. And for R2, that will just be the distance between Q2 and the value of Q, and the point Q rather. So that will be 0.3 meter. So many things changes for the second problem. Now, the next thing you need to know about this problem is that we need to know where the net electric field will be directed to. Will it be going towards the positive x-axis, or it will be reversing back to the negative x-axis? Well, according to what we are saying, we can see that E2 is much more closer to point Q than that of E sub 1. Definitely, since we know that according to the relationship between the quantity of charge and the distance between the charge and the given point is that the higher the distance between the charge and the given point, the lower the electric field. And the lower the distance between the given point and the charge, the higher the magnitude of the electric field. Therefore, E sub 2, due to the fact that it's much more closer to Q, then it's going to possess much more higher magnitude electric field than that of E sub 1. So therefore, the net electric field will carry a negative sign. So if this doesn't happen, then we are doing something different. So definitely the net electric field must have a negative sign. So let's see that. Okay. So right now, what we are going to do is to substitute. We know that according to the relationship, E sub 1 will be KQ1 divided by R1 squared. Then we are subtracting it from KQ2 divided by R2 squared. So right now I can substitute. The value of K is 9.0 times 10 to the power of 9. Then I'm multiplying this with the value of Q1. Q1 is positive 200 microcoulombs. So earlier we said positive 200 microcoulombs, which turns out to be 2.0 times 10 to the power of negative 4 coulombs. So that's 2.4 or 2.0. That's the same as 2 is power minus 4. Then I'm dividing this with then r sub 1 squared. That is 1.3. The z over here. I'm having 1.3 squared. Then I'm subtracting this from the value of K 9.0 times 10 to the power of 9. Then multiply by the magnitude of Q2. That one is negative 300 microcoulombs. So earlier in the first problem, we said negative 300 microcoulombs result in 3 times 10 to the power of negative 4. So that's 3 times 10 to the power of negative 4. So I'm dividing this with arg2. So arg2 squared is 0.3 squared, and that will be 0.3 all squared. So before I subtract these two values, then I would like to have their answers one after the other. So I don't need the diagram anymore. I can get rid of the diagram since we have the direction of each of the components electric field. So the net electric field E sub n will result. So I'm going to type this into my calculator in the first place, and that should result in 1.06, or let me say 0.7 times 10 raised to the power of 6. So I'm subtracting that from, and I'm gonna repeat this to 3.0 times 10 to the power of 7. So if you type this properly, you should get 3.0 times 10 to the power of negative 7. So I'm just going to subtract that from 1.07 times 10 raised to the 6. Then I should have negative 2.89 times 10 to the power of 7. And this is the magnitude of the net electric field. So now, since the net electric field acting on point Q is negative, then we can clearly say that our answer is absolutely correct. Number 2, 2-point charges at positive 20 microcoulombs and positive 1 microcoulombs are placed 10 centimeters apart. At what point on a line passing through these charges is the electric field 0? By the way, feel free to pause the video and check this question out. However, if you haven't subscribed to this channel, please do well to go and subscribe now. And if you find this video helpful, don't forget to leave a like or give it a thumbs up. And that's exactly what it tells YouTube that the video is liked, so you can recommend it to many viewers out there. Let's begin with the diagram. So assuming this is Q1 and this is Q2. Q1 possesses a magnitude of positive 20 microcoulombs. Q2 has that of positive 1 microcoulombs. The distance between Q1 and Q2 is said to be 1 centimeter. Okay, that's 10 centimeter, which should be the same as 0.1 meter. 10 centimeter divided by 100 will result in 0.1 meter. So I need a random point, but this point must be the point at which the net electric field is equals to 0. So what I'm going to take note is that the summation of the electric field acting on that point due to the both charges has to be equals to 0. So assuming this is the point, by the way, you can select any point, and I'm going to denote this point with an uppercase X. And therefore, the distance between Q1 and the point X will become lowercase x. And if that is the case, since the distance between Q1 and Q2 is 0.1, and the distance between Q1 and uppercase X is X, then the distance between Q2 and uppercase X will become 1 or 0.1 minus X. Perfect. Now I need the direction of the electric field acting on point X due to the both charges. So let's begin with the first charge, Q1. Since Q1 is a positively charged, Q2 is also positively charged, which knows that the electric field formed by a positive charge will extend away from the charge. Therefore, E sub 1 will extend toward capital X. And this is E sub 1. What about E sub 2? Since E sub 2 is also positively charged, then the electric field will also extend away from it and will make it to be directed towards the negative x-axis. And therefore, E sub 2 will be associated with the negative sign. And finally, E sub n, which is the net electric force, will be indeed equals to E sub 1 plus negative E sub 2. Now we can set that E sub 1 minus E sub 2 is indeed equals to net electric force. But we said at this point x, the net electric force is equals to 0. So therefore, E sub 1 minus E sub 2 is equals to 0. What if I bring E sub 2 to this side? That is, I add E sub 2 to both sides. We can clearly say that E sub 1 will be indeed equals to E sub 2. And this equation right here will help me to solve for the value of x, which will be the distance at which the net electric field is equals to 0. So, according to the definition of the net electric field, of electric field, we said it is given as kq over r squared, where r is the distance between the point at which the field is acting and the charge that is producing the field. So therefore, for E sub 1, that will be given as kq1 over r sub 1 squared. And for E sub 2, that will be given as kq2 over r sub 2 squared. So what is arc sub 1? What is arc sub 2? Arc sub 1 is given as x, which is the distance between the first charge and the selected point. And arc sub 2 will be 0.1 minus x, which is the distance between the second charge and the selected point. Now, let's begin the substitution. So, for now, I'm through with the diagram. I cannot get rid of it. So, therefore, I can have E sub 1, which is the value of k, multiplied by the first charge, which is 20. 20 microcoulombs is the same thing as 2 times 10 to the power of negative 5 coulombs. So I'm dividing this with x squared, which is the distance between the charge and the point x. And this is now equals to E sub 2. E sub 2 is expressed as k multiplied by the magnitude of charge q1, that's 1 times 10 to the power of negative 6. 1 microcoulombs is the same thing as 1 times 10 to the power of negative 6 coulombs. And I'm dividing that with 0.1 minus x, or the power of 2. So right now, what I'm going to do next is to cross multiply. So if I cross multiply, I can clearly see that k multiplied by 2 times 10 to the power of negative 5 will tend to be multiplying 0.1 minus x all squared. And this will be clearly equals to k multiplied by 1 multiplied by 10 to the power of negative 6 multiplied by x squared. So right now, I would like to allow variables to be at one side and constant to be at another side, typically values. So I'm going to divide both sides with k times 2 times 10 to the power of negative 5. By now, I should have begun the mathematics, but I don't just want to start that. I want to have everything to be expressed. But I don't think you should feel it's bulky this way. K times 2 times 10 to the power of negative 5. Hopefully, you're getting the steps. So this can cancel out, and I can have 0.1 minus x all squared to be equals to k times 1 times 10 to the power of negative 6 times x squared to be dividing k times 2 times 10 to the power of negative 5. So finally, for the last step, I would like to divide both sides with x squared. So I'm dividing 2 with x squared. That's multiplied by 1 over x squared. And this cancels this x, and I have x squared to be at that side. Now I have variables at one side and constant at another side. Now I can begin the substitution. However, I can clearly see that k can also get rid of each other as well. So let me create more space so that you can clearly see everything once and for all. So therefore, 0.1 minus x all squared divided by x squared will be indeed equals to 1 times 10 to the power of negative 6, all divided by 2 times 10 to the power of negative 5. Now, let's focus at the right hand side. We can see that it tends to be 1 by 2, then multiplied by 10 to the power of negative 6. If this comes to the front, or if it comes to the numerator, it will become a positive sign, plus 5. So which will be 1 by 2 is 0.5 times 10 to the power of negative 1. And this should be 5.0 times 10 to the power of negative 2. Perfect. So right now I can have 0.1 minus x all squared divided by x squared to be equals to 5.0 times 10 to the power of negative 2. Now, what I have at the left hand side are both perfect squares. I can just re-express them as this 0.1 minus x all divided by x, then all raised to the power of 2. This is the same thing as this. Keep that in mind. So this is equals to 5.0 times 10 to the power of negative 2. So finally, I would like to take the square root of both sides. So taking the square root of both sides is just like multiplying both sides with an index of positive half. So therefore, the expression can turn out to be, let me rule this so that you won't mix it up. So that will be 0.1 minus x all divided by x all squared multiplied by 1 over 2, and this is equals to the square root of 5 times 10 to the power of negative 2. So you can clearly see that this can cancel out, and we can have 0.1 minus x over x. So if that is equals to, now the square root of 5 times 10 to the power of negative 2, so I'm going to use my calculator for that. So that results in 0.22. So that's equals to 0.22. So right now we can just collect the like terms. Sorry, cross multiply rather. So I can have 0.1 minus x to be equals to 0.22x. So the next thing I'm gonna do is to bring this to the side, okay, so that I can always factorize the GCF out. Then with that I can always solve for x. So right now I can have 0.1 to be equals to 0.22x plus x. Since it is negative initially, when it arrives here, it will be positive. So that should be 0.1 to be equals to. So I'm gonna factorize the x out. I'll bring it out. I can even add that up. 0.22x plus x. 0.22 plus 1. That's 1.22. 1.22x. So finally, I can divide both sides by 1.22. So 0.1 divided by 1.22 result in the value of x. So 0.1 divided by 1.22 becomes 0.8. So the distance is 0.08. And this is the point at which the net electric field is indeed equals to 0. And that's it for this problem. Hopefully grab that. So it means it will be very close to the first charge. That is the first charge, 20 microcoulombs charge, since it is the highest magnitude. That's the point at which the net electric field will be equals to 0. Number 3. Two identical spherical balls, each of mass 0.3 gram, carry identical charges, are subtended by two threads of equal length. At equilibrium, they position themselves as shown below. Calculate the charge on either balls if G is equal to 10 meter per second squared. It turns out that we're having system of forces being impacted on these spherical balls. So therefore, we can resolve them. So since the tension force is directed towards this part, towards the northeast direction, and the electric force is directed towards the western direction. And for the last one, the weight force is directed towards the southward direction. Then we can clearly say that those forces tends to form a right angle triangle. So we can always resolve them. So this is the tension force that is unknown. This is the electric force that is unknown as well. And this is the weight force that is also unknown. So we need to calculate them. However, fortunately, we are given the angle between the tension force and the electric force, and that results in 60 degrees. Keep in mind, since the spherical balls are identical, so therefore they will carry the same charge, which implies that if we solve for this, then this is the same as that of this. Now, I would like to resolve the tension force. So using some of the functions of of trigonometric functions, we can clearly say that the weight force mg is indeed equals to the tension force multiplied by sine of 60 degrees, and the electric force F sub E is also indeed equals to the tension force multiplied by cosine of 60 degrees. So this will always help us to get the weight force, the tension force, and the electric force. And having gotten that, we can always get the magnitude using the definition of electric field. So let's begin. So to calculate the weight force, we are given the acceleration due to gravity to be 10 meters per second squared, and we're also given the mass of that object. However, the mass is measured in gram, so we will need to convert that into kilogram. To convert gram to kilogram, you divide by 1000, and that should be 0.003 kilogram. And to convert kilogram to gram, you multiply by 1000. So therefore, we can find the weight force, and that should result in 0.0003 multiplied by 10, and the weight force should result in 0.003 Newton. Now, having gotten the weight force, I can get the tension force according to this first equation, and having gotten the tension force, I can also get the electric force with the second equation. This question sounds very good. I like that. So right now, what I'm gonna do is just to substitute. So the weight force is 0.003, and that is equals to the tension force multiplied by the sine of 60. So what I'm gonna do right now is to divide both sides by sine 60. Then I have the tension force to be equals to 0.03 divided by sine 60. That's 0.0034. But I would like to approximate that. I have some values that is approximable after 4. That's 0.0035. So since it is tension force, so it's also measured in Newton. So lastly, I can find the electric force using the second equation. So we can clearly see that. So I would like to get rid of this. The electric force is equals to 0.0035 cosine 60. So I'm going to type that into my calculator. 0.0035 multiplied by the cosine of angle 60 degree. That results in 0.00175. So I'm just going to approximate that to 0.0018. And I have the net electric force to result in 0.0018 Newton. So now, according to the definition of electric field, we said it is equals to the ratio of the electric force to the unit point charge. But unfortunately, the electric field is not given to us. However, the electric force has been gotten. So we can use Coulomb's law to get the charge since the charge are identical. Now, back to Coulomb's law. However, if you haven't watched my video on Coulomb's law, you can check the description of this video, or you just click on the video that just pop out right now. Then you can always find everything you need to know about Coulomb's law in that video. So it says that the net electric force is proportional to the product of the charges and inversely related to the square of the distance between them. So it turns out that distance between the two charges is given to be 40 centimeter. 40 centimeter in meter is 0.4 meter. And the value of k is constant as 9.0 times 10 to the power of 9. And since the charges are identical, it means they carry the same magnitude, which implies that we can multiply them to result in q squared. So therefore, 9.0 times 10 to the power of 9 multiplied by q squared. So should I use uppercase or lowercase? Let me use upper. Divided by 0.4 squared. And this is equals to the magnitude of the electric field we just got. Of the electric force we just got. That is 0.0018. Okay, so let's just use our calculator. However, let's cross multiply first. So that should be 0.0018 multiplied by 0.4 squared. That equals to 9.0 times 10 to the power of 9 multiplied by q squared. Okay, I'm just used to that lowercase. So I will divide both side by 9.0 times 10 to the power of 9. So this cancels out. And q squared can result in, so let me type that into my calculator, 0.0018 multiplied by 0.4 squared. And I'm dividing that with 9 times 10 to the power of 9. So that results in 3.2 times 10 to the power of negative 14. So finally, I can solve for q by just taking the square root of both sides. So q will finally be equals to the square root of 3.2 times 10 to the power of 14. And the square root of 3.2 times 10 to the power of 14 result in 1.79 times 10 to the power of negative 7. And this is the magnitude of the spherical box. And that is it for this problem as well. Number 4. Two identical point charge of magnitude positive 100 microcoulombs are separated by a distance of 1 meter as shown below. At what point will the net electric field equals to 0? Part A. Part B. If the charge on Q2 doubles to positive 200 microcoulombs, where along the x-axis relative to the first charge will the net field be equal to 0? I intentionally didn't draw the diagram for you. I want you to use your own creative thinking. I want you to think by yourself and solve this problem. And you can share your solution with me in the comment section below for review. If you find this content helpful, please give it a like and comment your point of view in the video. So that is it for the video. Thanks for watching. See you guys in the next video. See you.